This is about backdooring a CPU, actually, not a firmware or microcode, but the logic of inside a GPU. Basically is assembled like a tutorial of how you will go backdooring a CPU. And that's what it is called deep submicron. Submicron is the name of technology, of the process technology of modern CPUs. When you go lower than 3,000 nanometers, about 3,000 nanometers, you start calling deep submicron technology. So let's start. Well, first we're gonna do a little review of the history of hardware backdoors. Of course, I cannot talk about all of them, but I pick up some samples about very famous hardware backdoors and through the history. And then we're gonna speak about two backdoors. The first one is about how to is a backdoor that allows you to get code inside your CPU, and the other one is how you get data outside your CPU. Basically infiltration and exfiltration. The infiltration is placing a logic backdoor inside the CPU, and the exfiltration is basically doing a Tempest attack, RF style attack. And I have a lot of demos. Let's hope everything works. So this is the first slide. We're going to talk about the different kind of backdoors. We have a lot of layers in a computing system. Regular rootkits go in kernel mode or user mode or maybe hypervisor. They are the most common kind of rootkits. You can place a rootkit in a firmware. You can place a rootkit in a microcode. In theory, and I never saw one, but it's possible. It would be very cool if somebody do that, but I never saw anyone. You can actually do a awakening of protocols like the random number generator. There is a very effective kind of rootkit. The backdoor. Very easy to detect, unfortunately, and they're really practical backdoors. They work all the time. That's why they are most common. But the problem is, it's very easy to detect them, and software defense are getting better and better and catching all this kind of backdoors. So backdooring is moving inside the hardware. It's like lowering the level to the hardware or the physics level. So OTAC will be very close to the physics, very close, like at the lowest level. But we're gonna see this actually, it really looks like a software because in a computer system you have software defined basically the world, all the layers. I don't think it's a really practical rootkit really, because it's very expensive, very difficult to do, and it's not practical like a software rootkit. But they have a lot of advantage being in the hardware. Well, let's first talk about the oldest one, or the oldest one that I could find. This is a very good rootkit, backdoor. Sorry. It was placed in the Great Seal. It's like a picture. It was like a wooden picture of the U.S. eagle that was in the Moscow embassy. It actually was like a microphone that it didn't have any power. It got activated by external radio frequencies. You got to illuminate with a radio frequency, and will modulate and emit in a different frequency. So it was very difficult to find. It was designed actually by Leon Theremin. It was a Russian scientific that created a lot of great television, created theremin. It was a musical instrument. And it was very cool. It was created in the 20s or the 30s. It's a very old technology. No, this is a very famous backdoor. It was created in the 90s by the NCA. The idea was to every communication device to have this encryption. It has a keyscrow mechanism, keyscrow meaning that basically the NCA of the government has the main key, a master key, you can listen to your communication. But it was so bad that actually not only have a key screw is completely is terrible for privacy, but also have a vulnerability that does have nothing to do with the key screw. It has a vulnerability on the protocol. So really, nobody adopted this chip. It was very easy to detect the backdoor. And this is a very modern backdoors or implants, as the NCA calls them. It was leaked by Edward Snowden. It have a lot of hardware devices that you can plant you in your machine. You have backdoors inside cables to form a kind of assisted tempest attack when they emit radio frequency. You can control remotely. They have a lot of different backdoors. You can the agents from NCA can order from free to thousands of dollars each one. Very interesting technology. It's not really new. These leaks are from 5 years ago, so you can imagine what they have today. And we also have hardware backdoors are really explore a field in academia. They have world conference about hardware rootkits. The one that I know is Host. They have a challenge. There's a university that every year run a challenge when they form two teams. One have to attack or insert a hardware rootkit. The other one have to defend and detect it. It's very interesting. They been 3 or 4 years. There's a lot of designs that are coming out from this challenge. And then you have some very academic, very theoretical attacks. Like this one is very famous when the guy basically modified a gate, a transistor, the dopant of a transistor, so it inserts a vulnerability in a random generator. It's almost impossible to see. But we're going to do a different thing. We're going to do a more simple, basically, rootkit. We're going to insert a big piece of logic code inside a CPU. Well, then you have, unintentional backdoors, I like to call it. When you develop a system, you always leave a lot of interface like JTAG, vendor-specific codes that helps in the development. And most of the time, development forget them. They are there. So you can use this. This is very difficult just to see if it has an intentional backdoor or was not intentional. Most of the time, it's not intentional. But it really acts like a backdoor. We have a lot of examples here. And let's talk about what we did. So we basically wanted you to do a backdoor like insert a piece of code in existing CPU, not a very small modification, but like a big brute modification to see how difficult it is to detect, because I couldn't find any example of a real rootkit, a real backdoor in a real CPU. That's really difficult to do because you usually don't have the code of a CPU. It's like the crown jewels of Intel and REM. You can see the source code of a CPU, so it's very difficult to find a backdoor for one. And I will tell you there is 2 rootkits. The malproxy rootkit basically is you can infiltrate code inside a CPU, and with the Rift you can exfiltrate data from inside the CPU. I'm going to do the demonstration of both. I'm going to run a simulation from the malproxy because I don't have $1 million to fab it, but I'm going to show you the designs and the complete process, how it looks like. And the radio frequency rootkit or backdoor, I will try to do a demonstration with the FPGA that I have here. I hope it works. This is very, very difficult because a radio frequency you can't trust it. But let's see, maybe it works. Okay, so the first backdoor is very simple. You can see here. It's basically a piece of logic. It gets in between the CPU and the bus. And it is constantly listening to the bus traffic. And when it locates a cookie or a specific password or a specific key that passed through the bus, it activates. And it lets you do basically two things: write into memory and read into memory. With that, you have basically a debugger. So you can, it's like a covered debugger. You can place code and read code from memory and put every kind of code you like into memory. It isolates the CPU for a couple clocks, so the CPU never know what happened. And then just release control back to the CPU, but the memory change. For this, we use a real CPU. We use an REM Cortex. It's one of the smallest designed for REM, but it's a real one, and it's actually used today. There are millions of this REM in every place. The bus is the AMBA bus. It's called it's an embedded bus. It's the most used in the industry. And the good thing is it actually works in FPGA, but also you can synthesize in a 45 nanometer process, or it's ASIC ready, as I'm going to show you. This is the high-level design. It's a very simple state machine. It's very small. It's very linear. You read the command, read the address, data, and execute. Then you see how I put this data in the bus. Well, you can do a lot you can place this data on the bus in a lot of different ways. For example, you can send a ping to the machine. The machine will, in some way, will copy the packet into memory. When they copy the packet into memory, inside the packet, this command is codified in like, in several words. And the rootkit is listening to this bus traffic and get activated. And this is it's a state machine. It's writing Verilog. Verilog is a language in hardware description language that you basically use to define the logic gates of a CPU. The REM CPU source code that we have is Verilog, so the backdoor is also writing in Verilog. We can see here there are the cookies. There's the magic numbers that have to pass through the bus to activate the backdoor. The backdoor is basically a bus operation. It's very simple. Just take control of the bus, write data, or extract data from the bus. Here is how it looks when we synthesize. I think this is 45 nanometers. I think this is the logic. It's not physical. This is how when you compile that code, it results in about 400 gates. And you can see a little orange points here. There are the gates, and the green line are the connections. I use a Cooper process. They are free. You can download the libraries for free. Very old, as you can see, 180 nanometers is a very old technology, like 10 years old, but it's the one that you can get for free. And another one, 45 nanometers, that is a little more new. But what we did basically is to measure the resources that the CPU takes with the backdoor and without the backdoor. You can see this is the Cortex is very small CPU. It's only about 9,000 cells. You know, a Core i7 has like millions of cells. Each cell has about 4 or 5 transistors inside. And the backdoor is quite big compared to the CPU. You see, the one is the backdoor, has about 10% of the resources, because the backdoor is really not optimized. So it's actually quite big compared to the CPU. It's very easy to detect. This is a picture of the CPU with all the layers on it. They have, I think this is a 6 layer. Yes, the 180 nanometers have you have the gates. That's the first layer. and then you have 6 metal layers, that is the interconnections. It's very similar to a PCB. In fact, the algorithms are the same to PCB mapping. And well, we are gonna to upload the Backdoor, so you can basically do a diff with the CPU code, and you can have the Backdoor if you want to analyze it. It works simulated in FPGA. It works in if you want to use a completely custom ASIC also. Well, of course, you need a license for REM to synthesize this. It's very expensive, but if you are a college, you can get it for free. If you are a college, you actually can manufacture for free, probably. Most colleges have arrangement with the fabs, but you can, not millions, but you can do hundreds of CPUs or hundreds of chips for free. They will do it for you. Probably I will try to do that. So I'm gonna do a demonstration of how it looks like, how easy to detect a backdoor. For this backdoor is basically the first one that I talked. I didn't waste any effort in try to hide it in any way. So it's quite easy to see. Let's try to see it. Let's see. Okay, so this is a 45 nanometers chip. It had 10 layers because when you decrease the size of the process, you can also increase the amount of layers. So you have a lot of layers. You can see from here, you can see that the backdoor is that part from is one piece of the CPU die is different. It's that one because the way the code style that you do. It gets synthesized in a different way. So you only by looking at it, you can see that there is some code that is different than the other. Let's see more closely. So this is very cool. I can spend all day doing this because it's like a video game. You can see here the different layers. Sorry. We can see here the different layers. The first layer are the gates, the ones that they are down below. And we can see the backdoor has to us a lot of more layers than the regular REM code because I suck at writing Verilog. So I don't write in an optimized way. So the compiler tried to do anything to put together my backdoor that is actually not completely is not optimized, so it actually results in a lot of layers, a lot more. Let's see how the regular REM code is. We can see this is the regular REM. We can see how optimized is it. It really doesn't need any more layers. It needs 3, 4 only, and it only works. But the backdoor really needs a lot. But that's it probably because an artifact because I basically didn't spend a lot of time optimize it. I used a lot of registers. That's why it's so big. When you code in a ASIC, you have to minimize the amount of memory that you use. I use a lot because I'm a software guy, so I don't know how to code for hardware. But the compiler actually you try to put it, but it resulted in a lot of layers. You can see this is a very cool visualization. Let's see. Here are the gates. Oh, sorry. You can see there's the small gate. These are 45 nanometer gates, and this is the connections. You can see the incredible complex. This is the smallest CPU. But for example, we can see the 100 nanometer CPU is much more difficult to see. It only have 6 layers, so the compiler couldn't put more layers. And the backdoor in this process is almost impossible to see. Let's show you. Well, I don't know if you can see anything, but I can't see absolutely anything of this. You basically need some kind of software like IDA for ASICs for this because it's impossible to see. But it really depends on a lot of factors, basically the process. If you can see more closely, we can see that the gates are much more farther away because it have much fewer layers. The transistor have to be much farther away. So this is really not so optimized like the first process. Okay, so this is how, by visually looking at it or analyze it, you can see that a modification is quite easy to see. Of course, I didn't code the backdoor in a styled way, so probably if you code a little more, if you code with a little stilt in mind, you can make it much more difficult to detect. But well, this is a first try. The file that we are looking at is a GDS3 file. This is a file that you basically send to the fab to get it manufactured. Of course, this chip is missing a lot of verifications or a lot of steps that you really need to make it manufactured. For example, I don't have any power connection. I don't have any terminal out. It's just the die. So, but it's just for showing how it looks like. So this is the format of the word that have to pass through the bus, so it can pick up by the backdoor and execute code. As you can see, it's very simple. Just a command is read or write. It's a one single an 8-bit command, an address and data, and then a final command that means execution. When you execute, the backdoor disconnect the CPU because the backdoor is in place between the bus and the CPU, so it disconnected, execute the command, and just activate the CPU again. The CPU never know what happened. So this is an example that we can how we can activate this backdoor. Just a mem copy. You can see this code. It doesn't have any vulnerability. It's just a simple mem copy. But this where letters there is how the backdoor is activated. This is a command in code here in these bytes. Just by copying this string into a buffer, I force this data to pass through the bus, and it get detected by the backdoor and get activated. Of course, we can do it by mem copy, but can also do it by any way you can put place into the bus. There's thousands of ways to put data in the bus. Let's run a simulation to see how this works. We're going to simulate the world CPU. We're going to emulate with a emulator. It's open source. It's called Icarus Verilog. Because the ARM code is so simple, it's very fast. It doesn't run in real time, but it's very fast. You don't have to wait a lot to see the results. We are using, of course, an operating system, a firmware with a real-time operating system. It's called GPOs. It's because the CPU is very small, we have to use a real-time operating system. So there is booting. And we can see it could take a couple seconds to boot the world CPU emulator. And here we go. The first one is hello world. And then you do the mem copy. And the second one, we can see that the backdoor has modified the first hello with the word hack. And if we see the source code, we can see that there is no way this can happen because it's just a mem copy through a buffer. There's not anything that modifies the string, but the backdoor just got activated, modified the string. It actually is a read-only string. You can modify it anyway. But it got modified. And this is a simulation it's very fast, from Verilog. So we can see how many clocks it actually take. It took like, 10 million clocks simulated. It's a really fast simulation. And well, let's continue. This was the backdoor. So this is a way that you place a backdoor and you can get data inside the CPU. It's of course not the only way. There are, I don't know, thousands of ways, whatever you can imagine it. But I wanted to do one that actually really works, and how it looks like physically when you look basically at the chip. And of course, for that, you need the source code of the CPU. So you can synthesize it. The source code is, how to say it, is very difficult to get. but I can see it. I actually got it. This is a shortcut from REM CPU. I can see it. It's very easy to get. You only have to ask REM, and they will give it to you for free, if you are college, of course. But we have a friend college, which that basically borrowed us the code. And we can see this is the rootkit. We can hear this is actually I put a lot of documentation on it, so you can see it and understand it. It's very small. It's a state machine. You know, it's a case with a state machine. You can actually have a lot of prints, so you can debug the rootkit and see how it works. It's very cool. So the next one is once you are inside, how you take data out. Well, basically, you can do it with the network. But what if you don't have access to the network? You are air-gapped or something like this. Well, you can use the old NCI trick, the Tempest. You can emit bits using side channels. You can use sound, vibration, whatever. But we choose radio frequency that is the easiest to use. And this demonstration is a particularly fun one because we use the LEDs to emit radio frequency. Because basically what we do is once we have a backdoor inside, we just switch on and off the LEDs. 100 megahertz, that is a lot of speed. The LEDs can switch on and can switch at 100 megahertz. It's just turn on, but a lot of radio frequency emission the board will emit a lot of radio frequency from the PCB traces that basically are like small antennas. So you can exfiltrate data this way. Of course, nothing new, but it's very funny to see working in an unmodified board. This is a board that I'm using. It's a FPGA, but it's not modified. It doesn't have any kind of antenna or any modification. And we can see how we can emit radio frequency in basically in a lot of different frequencies. And we're gonna pick it up with this. This is a small software radio. It's a very cheap one, about $20. It's a TV receiver actually, but you can hack it and convert it in a software radio. It's only a receiver, but it's only that the only thing that we need is a receiver, because the emitter is the board. So this is how it works. Basically, when you switch on and off a PCB about over 100 megahertz, you send a square wave, but the square wave actually is composed of a lot of harmonics. There are sine waves. This is basically Fourier theory. So if you send a signal, what are you doing is sending a lot of different frequencies, and we only have to pick one, whatever, the fifth harmonic, tier one, whatever we want, and listen on this frequency, and we're gonna emit data or exfiltrate any kind of data using radio frequency. The range is pretty good. I can show you, but I tested up to 5 meters and works perfectly. The problem is you can't use any fancy modulation. You have to basically turn off and on, and you do some kind of amplitude modulation. It's very simple. Maybe you can do phase modulation with a more exotic kind of encoding, but this works, so I'm going to show you in this way. We can see how the more high frequency is, the more the signal get lower and lower and lower, but there is no problem because if we emit 100 megahertz and we use a frequency at 700 megahertz, actually this is very easy to listen because nobody is using the 700 megahertz frequency. So it's basically a void. We can very, very easily pick up the signal of the 700 and 900 megahertz. Even is much less power in there. Of course, we can run a simulation of the PCB, how the field is how it looks, the radio frequency field, the power field. We can see something very peculiar here is that we use a lot, if we don't use a single PCB, but we use 4 or 5, we actually use 8 because we have 8 LEDs. So the field is actually directed because it looks like a Yagi antenna. It's like a Yagi, some kind of Yagi formation. I'm really not expert in radio frequency. I just run this simulation using an upper source radio simulation. It's called numerical electromagnetic code. You can download and program and use it. It's very cool. And here's how you define an antenna. Here is the 8 PCBs defined. Very simple. You basically you code the points, and the program you set up the frequency, and the program will show you the field. Let's see if it works. How it looks like, because it's very cool. You can use it for a lot of things, not only for doing backdoors. Let's see. All right, so here is the like a 3D representation of the PCBs. Of course, it's much more complex than this. It's actually the PCB is not a straight line. It's more like it's in some kind of form, but just didn't have the time, so I did a simplification of the lines of the PCB board. So let's see the radiation pattern. We can see here how. But 100 megahertz, this is the radiation pattern, is quite directional. You can see that it's in one single dimension because the other one, PCBs at the side, acts as a Yagi antenna. We can see how the direction actually change when we change the frequency, because we are not transmitting at 100 megahertz, we are doing at 700. So let's play. This is a very good animation. We can see how it changed. We can see that at about, okay, we just 1700 is too much, but if we, when we increase the frequency, the antenna gets even more directional and it sends more power to a single direction, so we can basically point our antenna for avoid detection or whatever. And this is a very cool program. Okay, let's take it because I miss a lot of for example, I didn't simulate a ground plane that will modify somewhat the simulation, but it's from just an idea of how the field, where it points, basically. But actually, I run a real measurements or see if it's real, if the field has this shape. So I put a table, put the board in the middle, and start measurements around the table, and the result is this. So it's not really similar, but it's approximately the same way. We can see that actually it points where you have to point. I really need to do a lot more measurements, but we can see that it's approximately the shape is directional. That's the power, and at the angle, basically the antenna is in the middle, and I measurement the power at different points in a circle. So it really looks like simulations. Simulation is pretty accurate, and this is something that I didn't try, but it's very very interesting because by using different PCB lines, we actually can point the electromagnetic field in real time. This is a simulation of the 8 PCBs, but applying power to just the LED 1, the LED 2, there is a field the LED 1, LED 3, 2, 4. We can see how the field actually change direction. So if the backdoor actually can emit, can exfiltrate, can choose the direction where you can exfiltrate. I really didn't try this, but the simulation is quite accurate, so it probably will work. But we can try it right now. Let's see if it actually works. I have let's see. I have this FPGA board here. If you can see, this is the FPGA. Let's see if we can see the output of it. You can see The FPGA has a 8, it's basically a simulation of a x86 CPU. We can see here. Let's turn it on. There you go. It's booting the OS. It takes a little while. So this is running inside the FPGA. It's actually it's not a real CPU, it's a software CPU. It's only 16 bits, but it's only to show you that actually it's actually a working system. And I have a keyboard. Sorry, but the FPGA is very old technology, so I have to use a PS2 keyboard here. So if I push a key, actually you can see you have all kind of hardware emulated. You have memory controller, BGA controller, keyboard controller. And the thing about the keyboard controller is that the backdoor is inside the keyboard controller. So if I put a key, actually the scan code from the keyboard will get exfiltrated using radio frequency. I can show you right now. If I press a key, you can see how the LEDs flash. Well, they're flashing actually at 100 megahertz. So I am emitting each key I press are actually being exfiltrated. I emitted a lot of frequency, but we cannot see it. Of course, we don't know rise. So we're gonna switch the radio, see if we can pick it up. Let's see. There you go. Oh, perfect. Okay. Let's see. Let's try this software. This is very cool. I don't know if it works perfectly. This is the radio frequency spectrum of 700 megahertz. I was told you 700 megahertz is I think is the fourth harmonic. So we can see here when I press a keyword, when I press a key, how it actually emits a lot of radio frequency. It's actually a lot. It's probably illegal to emit this kind of power. But for example, if we use another frequency here, you can see there is almost no frequency here because it has to be an harmonic. For example, 900 megahertz also work. Well, it doesn't work very good. Let's try 500. There you go. There are different harmonic of a square wave. So the radio frequency is there. Let's try to decode. Let's see if I can. Oh, excuse me. I have a small graphic here. It doesn't look very good because the terminal is too small. Let's see if I can fix it. Oh, there you go. Well, if I press a key here, you can see it can actually listen to the encoded keyword. If I press the I key, it's actually had too much power. Let's see if we can get it a little better this way. No, maybe it's too close. Ah, there you go. Let's see. Let's press the escape key. No, it doesn't. No, that is horrible. Of course, I'm not the best, radio frequency engineer in the world, so I had to wiggle a little bit antenna. Sorry about this. Let's see. Escape key. Yes, I pressed the escape key. Okay, let's try the 1. Not the 1. The 3. Well, close enough. Yeah. True. Good thing the scan codes are really close from each other. Let's try the V. V key. 0. No, it's not 0. Let's try it again. S. Closer and closer. Well, you get the idea. It's actually V key. There you go. Well, it works. I suck at demodulation. But well, you can see we can pick it up pretty easily. If some competent guy do this, it probably will work much better. So there you go. This is the demonstration, the final demonstration. So you can exfiltrate a key. Well, that's it. If you have any question about this, I'm sorry it was a lot of information very quick, but that's it.
That was very cool. Questions, anyone? Thanks. My question isn't directly related to the security backdoor, but is related more to the FPGA stack you used. What platform did you use to deploy to the FPGA and to generate the bitstream? What platform did you use?
Yeah, your question is what is this? What platform I use for the radio frequency rootkit, right? Backdoor.
More so, what platform did you use to generate the bitstream? Was it a Xilinx or?
Yes,
like,
no, it's an Altera. It's an Altera D1 from TeraSig is the board, and the compiler is Quartus. It's a free compiler, actually. You can download it for free. It's this one. Actually, I think I got loaded because I was debugging it. Here, this is Quartus 2. You can download it for free.
And also, I wanted to know, from a security point of view, what vector do you see? Because essentially, you are generating erroneous hardware, right? So the only people who have access to generating hardware would be the hardware manufacturer. So what scenario do you see this backdoor actually affecting CPUs?
Yes, this is a great question. You are asking if this is real, what is scenario, what is this real application? Exactly. Well, actually, I was talking with a couple guys from Intel and AMD about this. They are saying that this is impossible. We can never get pwned and get some hacker place code inside our code. That means that, of course, it will happen. But the thing is, they are really, they have fear. Actually, they form a cybersecurity, best friends, best hardware friends. They fear that the very small ARM companies, they specifically name Rockwell. Rockwell is a ARM manufacturer in China and Taiwan. I think this is in Beijing. They have like 5-person shop, so they really don't have any security whatsoever. They are very, very vulnerable in security. So basically, the guys from Intel say, okay, it will never happen to us, but ARM, there are thousands of vendors. And this is, of course, an example of an ARM. If I can get the code, so anyone else can. That is the scenario. Basically, a hacker attacking Rockwell or, I don't know, any other ARM manufacturer, small ARM manufacturer.